Welcome back, everyone. In this video, we're going to talk about finding bounds for parameterized curves and kind of fit that a little bit into the context of integrating over curves. So I guess when we integrate over curves, we've got two different things that we've really looked at mostly. The first of which is just kind of your standard line integral over C of some function f ds. Which is equal to the integral. We have this formula from a to b f of r t times the length of r prime of t dt. And then our other option is when we're dealing with vector fields, and we have an integral over a curve that's lying in a vector field of f dots dr. These are both vectors, and then that's equal to integral from a to b f of r of t, and then times or dot product with r prime of t dt. So these two look really quite close. They're quite similar, at least in like concept and motivation for how these two formulas get put together and where they come from and stuff like that. But because of this, we wind up with, we need a parameterization in both case for the curve. I will never write this word and not run out of room. Okay, parameterization that we call r of t of the curve C that has bounds on t, a, and b. Okay. So this video today, we're going to talk primarily about how to parameterize your curve and then determining the bounds. So that way you're able to use this information in these two kinds of integrals right here and kind of see how they fit in. So let's go ahead and jump in with some examples. For our first example, we're going to look at our curve being a line segment between 2 points. So we're going to go from 1, -2 to 3, 5, and we're going to parameterize this curve. So when we parameterize line segments, what we're going to look for is r of t to be equal to some starting point p plus t times a vector v, where the vector v is just how we're changing between the 2 points. So p is our first point, q is our ending point. And so what we're going to get here is, so we have 3 minus 1, which is just 2, and then 5 minus -2, which is 7. Okay. So here, I just got to plug this information into here. I'm going to get 1, -2 plus t times the vector 2, 7. And if I kind of squish these together, I'm going to get 1 plus 2t and -2 plus 7t. So this is my parameterization for the curve C, but I only want this line segment to be going between these 2 points. And in order to do that, I put bounds on t that are between 0 and 1. And this is really just what you're going to use anytime that you're looking at a line segment that has been defined for 2 points here. So because this is a line segment between 2 given points, 0 is less than or equal to t less than or equal to 1. And the reason behind this is that if you take r of 0 and plug this in, well, we're just going to be left with 1, -2, right? Because this whole piece drops off. And then if we take r of 1 at the end of t, or like, I'm done traveling along this line segment here at t equal to 1, my final time, I'm going to get, well, 1 plus 2 times 1, and then -2 plus 7 times 1, which gives me 3, 5. And that's my ending point. So that kind of makes sense that at the beginning of my time t equal to 0, I am starting at the point that I'm starting at, and then at t equal to 1, which is where I want to stop, I get the point that I wanted to stop at. So that kind of gives me my bounds on that. So if I wanted to think about this in terms of putting this into an integral, what that would look like, so suppose I'm integrating over this curve of, I don't know, we could say y ds, for example. Well, the goal was integral from a to b of my function at r of t times the length of r prime of t dt. And so my bounds then would be from 0 to 1. My function is y, so I just go back up to here and I take the y component from that, -2 plus 7t. And then I really just have to look at the length of r prime. And r prime in this case, when we're working at the line segment, is always just this piece right here. It's my slope off of each of these two components. So it's going to be 4 plus 49, whatever that simplifies down to. And then you would just compute that integral right there. So that's kind of how you work with a line segment. Another popular one is going to be like, ellipses and circles and stuff like that. And so I wanted to do an example with an ellipse in this case. So our curve is equal to the set of x, y, such that x squared over 25 plus y squared over 4 is equal to 1. And we're going to do the part where x is greater than or equal to 0, and we're going to have clockwise orientation. So generally speaking, when we're parameterizing these kinds of things, be it a circle or be it an ellipse, we're looking for our x component to use a cosine and our y component to use a sine. But since we want a clockwise orientation, we're going to use negative sign instead. So just a little note here, this is for the orientation. So when we're working with an ellipse, our r of t is equal to, we just take the square root of whatever is below x and attach it onto the cosine. So we're going to get 5 cosine of t. And the same idea here with the sine, but don't forget the negative. So that's our parameterization. This negative here accounts for moving backwards through our curve, which is great. The big thing becomes now, what do we want for our bounds on t to be? And we can kind of sketch this region and take a look at what we're dealing with here. This is, so 2, -2, 5. This information all comes from what's right here. And we just want the half where y is greater than or equal to 0. So that's going to be this piece here. And since we have a clockwise orientation, we're moving in this direction. And this is 0. We can do pi over 2 up here. Pi over 2 is down here. Or negative pi over 2 is down there. And it might be really tempting to say, okay, I'm starting up here at pi over 2 and I'm moving down to negative pi over 2. But the thing is that we're actually already, the moving backwards part is already taken into account by flipping the orientation right here. So we actually can just simply say that t is moving between negative pi over 2 up to positive pi over 2. No further action is needed to make sure that we move in this direction right here. Taking this negative right here will take care of that. So we just put from negative pi over 2 up to pi over 2, but then putting the negative here guarantees that what we ultimately wind up doing is tracing the curve backwards, okay? If you account for it twice, you'll wind up canceling out the effect that you have. So, and this is really the best way to account for your orientation. I know it might be tempting to just kind of go ahead and flip this, which works as well, but it's not technically quite the right thing to do. This is really the route that you want to stick with whenever you want to change your orientation. So yeah, the big thing here to keep in mind, keep these in the order that you normally would. This negative here will take into account the fact that we want to move backwards. So that said, if we wanted to look at an example of integrating over this curve, we can say x ds or something. So then the goal would have been to take a b of f of r of t times length of r prime of t dt. Then we have the integral from negative pi over 2 to pi over 2. And then x at r of t is going to give me 5 cosine of t. And then length of r prime is, well, my r prime here would be equal to -5 sine t and then -2 cosine t. So then I would get times the square root of 25 sine squared t plus 4 cosine squared t. And then there's going to be a dt there at the end that I ran out of space for. Come back. So yeah, this is how you would fill that out if you wanted to try to incorporate this particular curve into some form of an integral. So. Okay. One final example that's pretty popular format-wise is when you're told that your curve is kind of a portion of a graph. So we're looking at the graph of y equals x cubed for x being between -1 and 2. So what you're kind of looking at here is, so if this is our curve, x cubed, we're looking at this curve right here. Okay, just like this portion of the curve, that little stretch. So we're going to parameterize that starting here, and we want it to move up to that direction. So in this kind of setup, what we wind up doing is just a really simple substitution. We say x is equal to t and y is equal to t cubed. So then r of t is equal to t cubed. And since x is equal to t, bounds of t are the same as the bounds on x. So that means that we have that t has to be between -1 and 2. Now, a word of caution. Sometimes bounds are given in terms of y. So you may need to solve for them. You can either solve for bounds on x and then use them for t, or you can do some sort of a direct substitution here and solve for them for t directly. Either way is fine, but just be aware that sometimes you're given them in terms of y, and you may have to solve for them in terms of x then. But anyway, this is all the information that you would then need to be able to do an integral problem. So if we wanted to look at, say, the integral over the curve that we're given here, but then we're going to work with we could work with a vector field instead if we wanted to, because I know the other ones we've looked at have just been pretty simple line integrals. Well, this is what we're going for here is the integral from a to b of f of r of t dotted with r prime of t dt. Notice that we have a dot product here, so we get a dot product here. We're not taking the length anymore. And this piece right here is f, your vector field. So our integral from a to b, we're going to use the bounds on t. F of r of t, I just replaced my y value here with my y value here. So I'm going to get t cubed squared and then 3 times t. And then I dot that with r prime, which I'm just going to compute directly here. It's going to be 1 and then 3 times t squared dt. So you would take that dot product and then you would just compute that integral. This one would also wind up being fairly straightforward because you're just going to get a polynomial after you take that dot product. Not too bad. So, but anyway, this is kind of how you find some different bounds when you're parameterizing curves, and then a particularly tricky one when you're looking at a backwards orientation there. But yeah, so that's pretty much it for this video. I will see you guys next time.